Hey, let's look at this table here, right? The table we have here, we have the delta function. This is the translation in pairs. So we know the transform pairs. The Laplace transform of delta t is 1 and ut is the transform of ut is 1 over s. And that's based on definition we actually carried out that integration, right? The other ones, this one, the third, this one we did using the integration property, we get this one, right? And if you apply this, the S-domain translation property to that one here, and you will get this one. And if you apply the Laplace, translation property to this one, you replace S by S alpha, you get this one. And we did a cosine, right? So this one we already did. And if you multiply this e2 minus alpha, again here you will replace that s by s alpha. So in this case, you replace both. And we didn't do for the sine. So let's do a couple of ways for the sine. This is going to be the kind of, what I call it, the bonus clip, right? So this is the more interesting one. So let's do a sine. So we can do the sine omega t. Let me use omega instead of beta. I don't really like to use beta for the frequency, although the text use that. So let's see the Laplace transform of sine omega t ut, and that's going to be equal to the as we did before, right? As we did before, we could do the sine using the Euler and then the cosine e2j theta. So this video clip may be a little bit long again. I'm sorry about that. E2j theta is going to be cosine theta plus j sine theta, and so therefore the imaginary part of this one here is going to be equal, sine theta is going to be equal e2j theta minus its conjugate. If you watch the video, e2j theta minus e2 minus j theta divided by 2j. Right, so that's the imaginary part. Or you can just do the e2 minus j theta. That's going to be equal cosine minus 2 minus j times sine, and then you subtract the e2 minus j theta from e2 j theta. You're going to get a 2j times sine theta, and so you can divided by 2j on both sides, you get this as well. But in any case, so let's see, this theta is just equal sine. So this one here is the 2j e2j omega t minus e2 minus j omega t. So we treat omega t and theta, and in this case times ut, and this Laplace transform based on the linearity property, we can break this into two. So we have 1 over 2j and the Laplace transform of e2j omega t times ut, and here minus 1 over 2j times the Laplace transform of e2 minus j omega t times ut. And again here we will apply the S-domain translation property. That's going to be 1 over 2j, and times the S-domain, the first one here, we replace s by s minus j omega, because this e2 minus alpha t is e2 j omega t. So therefore the alpha is negative j omega. So we replace that s by s alpha, replace that s by the s minus j omega for the first term, right? And the second term here is 1 over 2j, and we replace that by s plus alpha. In this case, alpha is j omega, so s plus j omega. And so in this case, we will have, let me do this in 2 steps rather than in 1. So this may just take a little bit longer time, but so let's see, s minus j omega, s plus j omega. Right, so I multiply the numerator also by s plus j omega. For the second part, I have s plus j omega, and I multiply by s minus j omega. I do the same for the numerator, s minus j omega. Right. So in this case, you see this. So now I can add these two parts together. So in this case, I have 2j, and I have s minus j omega. By the way, s minus j omega and times s plus j omega. Let me just write this. This should be s plus omega squared, because the complex number and its conjugate multiplied by its conjugate is just the magnitude square. And in this case, I have s plus j omega minus s minus j omega. So in this case, the s is going to be canceled, so the j omega is going to be doubled. So that I have a 2j omega here, and 2j will be canceled by this 2j. So there I have s squared plus omega squared plus s plus omega. Sorry. So this is the Laplace transform of the s omega. Let's see, compare this with in the table. Yes. So table uses beta. So this is correct, right? So let's see. Alternatively, I could use the differentiation property. So the differentiation property is saying, let's see, if we know, let's see, so this is the method 1, right? The method number 2 is, let's see, I already know the Laplace transform of a cosine omega t is equal to s over s squared plus omega squared, right? Let's see the sine omega t. We know the sine omega, let's say d omega t, d cosine omega t dt, we know that is equal negative omega times sine omega t, right? So therefore, the sine omega t should be equal to negative 1 over omega d omega t d cosine omega t dt. And how are we going to utilize the S-domain translation property? And this one here, the Laplace transform of this one here, therefore the Laplace transform of sine omega t should be equal to the negative omega t, negative omega, and d cosine omega t dt, the transform. So that 1 over negative 1 over omega, the Laplace transform of this, the derivative. And we know the Laplace transform of this one here based on the differentiation property, that should be equal to s negative omega s times the Laplace transform of omega t, which is s over s squared plus omega squared, right, minus 1 minus cosine omega t omega times 0, that's equal to 1, the initial condition of that function, right? So therefore that's equal to 1, not 0. So I'm minus 1 here, so therefore I have 1 over omega times, so I have s squared plus omega squared, and I have s squared on the numerator minus 1. So therefore, in this case, I will get s squared times a negative here. So I get what's on the numerator inside the brackets? That should be negative omega squared, right? So negative omega squared divided by omega, I got a negative omega. I have a negative 1 outside this, so this will give me omega over s squared plus omega squared. You see this, the interesting part of the translation properties. They actually kind of talk to each other really nice. Another example is, let's see, we did the translation property is for the UT, right? No, the derivative property. Let's see the UT. We know the translation property. Well, this guy here is 1 over s, right? And delta t, another way of think about delta t is that's just a derivative of ut over time. And if you use this one here, actually the Google Colab, the same pi actually utilizing that. And so in this case, therefore the Laplace transform of delta t is just equal s times the Laplace transform of ut and minus the initial condition ut minus 0. And in this case, then that's s times, we know 1 over s minus 0, so that's equal to 1. So you see everything kind of coming together, right? So this is really the good thing about the translation. I mean, all these the properties of Laplace transform. Make sure you understand those. Okay, so these 5 video clips, including this bonus one, will conclude the lecture number 8. I hope you understand these. So whatever you do, remember, you just keep going, never stop. Okay, see you next.